Hello, I'm Dial Holton, Microcalorimetry Product Manager at TA Instruments. I would like to welcome you and thank you for joining us today at this webinar. If you get disconnected at any time, please use the instructions you received to log back in. You can access various content by clicking the document widget at the bottom right-hand corner of the screen. This includes speaker bio and additional file downloads. And if you need any help at any time, click on the question mark widget. Please ask any questions you might have at any time during the presentation by submitting them through the Q&A window. We will answer as many of these as possible at the end of the webinar. Our presenter today is Dr. Malin Serkusk. For the last 10 years, Malin has held a position of Product Manager and Applications Specialist at TA Instruments. She holds a Master's of Science degree in Biochemistry from Stockholm University and a PhD from the University of Lund in the laboratory of Professor Ingemar Wadzo. She has worked extensively with differential scanning calorimetry and isothermal titration calorimetry, as well as other biophysical methods. Her early work in microcalorimetry instrument development included responsibilities in product management, application lab management, and marketing at Thermometric in Sweden. She is considered the world's leading expert on TAM isothermal instruments with numerous microcalorimetry publications, and in 2014 was recognized for her contribution to the field of microcalorimetry and featured as a biophysicist in profile by the Biophysical Society. The title of her webinar today is TAM Air, a versatile isothermal calorimeter with high performance and robustness. Malin?
Thank you, Dial. So today's webinar will be about a versatile isothermal calorimeter with high performance and robustness, the TAM Air. TAM Air can be used or mainly used in the cement and concrete area, but can also find use in application areas regarding food and environmental science. So the webinar today will first start by introducing calorimetry to you, and then it will cover the instrument and how that is built up, and finally we will go through some applications that TAM Air can be used for. So if we start with the technique, isothermal calorimetry. First, I just say isothermal means that we are not changing the temperature, so we keep the temperature constant over all times. Calorimetry is a universal technique. Virtually any processes, biological, chemical, physical, will either produce or consume heat. And calorimetry is the technique that actually measures this heat production from a sample. It's non-specific, which means that we can study almost any kind of processes, biological, physical, and chemical processes. So a heat flow calorimeter, which TAM Air is, we measure heat flow, and that's denoted dq dt. So it's a rate, it's how quickly heat is transferred over time. Heat flow is directly related to the heat production or consumption rate in the sample, and that's denoted P. P and the Q dt is measured in watt, which is joules per second, and again you have the rate, joule produced per second. And a microcalorimeter by definition is a calorimeter that measures heat flow in the microwatt range. It could measure more, milliwatt, and it could measure smaller in a nanowatt, but it's by definition that the range is in microwatt. It has nothing to do with the sample size. It can still be very big samples and still be measured in a microcalorimeter. The heat production or consumption in a calorimeter or from a sample is denoted P, and it's equal to the enthalpy of the reaction rate, and the function of the concentration of the reacting species inside the calorimeter. So it's a very information-rich equation we have here. We can get thermodynamic information from the enthalpy. We can get kinetic information from the reaction rate and the rate constant. And we can get analytical information from the concentration factor in this equation. We are visualizing the heat flow by plotting the heat flow, either normalized by weight or some other factors, or as just heat flow. And that's on the y-axis, and on the x-axis you will have time, and time will be in minutes, hours, days, and sometimes also weeks, which you can have on the x-axis. At any time in the plot, you can go in, and that is the signal there is reflecting the the reaction rate at that point. So it's directly related to the reaction rate of the process under study. Also note that the measured heat is the total heat of what's going on in the sample. So it's the sum of all the ongoing processes. If we integrate the curve, we get the heat, the total heat out of the reaction. And then if we integrate joules per second over time, we get joules. And if it's normalized, we have joules per gram, which we plot on the y-axis. And that's again plotted against time. And here, the total heat of the reaction is then related to the extent of the reaction under study. So the benefits of calorimetry is that we can measure all kinds of processes, chemical, physical, biological. It's a non-specific technique, meaning that we are measuring everything that goes on in the sample, so you do not have to specify the response you're expecting and what you're going to analyze afterwards. If there is something going on, you will measure that in the heat flow calorimeter. It's non-destructive, so if you see there is something going on, we have not changed the sample in any other way, and you can take it out of the calorimeter and do further analysis afterwards. It is not depending on the physical shape of the sample. Anything you can fit into our sample handling ampules could be put into the calorimeter. There is no need for sample preparation, but of course you could do if you need to have more specific measurements, but you can just load your sample into the calorimeter and measure the heat output. It's direct and continuous, which means that you get real-time data and not snapshots over the time. So that was a very brief introduction to what calorimetry is, and now I would like to talk a little about the instrument itself, the TAM Air. First, if we start with the history, TAM Air was initially introduced in 2000, where the first TAM Air was actually specifically designed for the study of cement hydration. It was an 8-channel calorimeter, the same type we have today, with 20 milliliter sample sizes. It has a simple data logging software. The temperature range was up to 60 degrees, and there was an external calibration procedure. 2 years later, we introduced a second TAM Air, where we just moved the calibration procedure to an internal one. At the same time, we also introduced what we call the add mix ampule, which allows you to add and mix sample inside the calorimeter to not miss the initial reaction. 2005, the third generation TAM Air was introduced, where we increased the temperature range up to 90 degrees of the TAM Air. And 2006, there was a new software, TAM Air Assistant, that both performs the experiment and can help you in analyzing the data, was introduced in 2006. Also a new calibration procedure that we use still today. In 2012, we introduced the 3-channel TAM Air for allowing bigger sample as concrete samples. So you have 3 channels up to 125 milliliter. And now this year, we introduced the 5th generation TAM Air. It's a new design, state-of-the-art electronics, and gives us much better stability of the baseline from the TAM Air. We can also see on the TAM Air publications that was starting in 2000 up to May this year, that we have over 1,200 publications for TAM Air, and over 900 of these are for cement and concrete research. So that's the main application area of the TAM Air, even if we see use in other fields as well, which I will mention when I come to the application parts of the presentation. So if we look at the calorimeter itself, it consists of a thermostat and a calorimeter. It's an air-based thermostat, so flowing air will control the calorimeter temperature and will minimize the outside temperature disturbances that will come from the laboratory environment. All the calorimeters are held together in a single removable block, either with 8 or 3 individual calorimeter channels, and these blocks are user interchangeable inside the thermostat. Each calorimeter is a twin heat flow calorimeter, and we have both the sample and a reference side for the measurement of the heat flow. I will show the calorimeter parts in detail. So if we start with the one twin channel calorimeter, this is a picture of the 20 milliliter calorimeter. You have the ampule holder, and that's where you're going to put your sample into. The ampule holder is mounted directly to the heat flow sensor and connected to a primary heat sink. All other surfaces around the ampule holder and the ampule are air, so that's isolation, which means that we channel the heat flow to go through the heat flow sensor in the bottom. This is the sample side you are seeing cut away, but the reference side look identical. In the reference, you will have an inert sample. You will match it by heat capacity, but there should be absolutely nothing happening in the reference. In the top, we have a secondary heat sink that will channel away all the temperature disturbances that come from outside. So we isolate the calorimeter, the sample, to just transfer the heat through the heat flow sensor in the bottom. So these calorimeters are then assembled, in this case in an 8-channel block, but also the 3-channel calorimeters will be assembled in a block with 3. And you see in the bottom, that says no contact. That's where the primary heat sink is, and the sample is actually standing onto that. There is no contact between the calorimeters in the bottom part, so we will minimize the crosstalk between the channels. In the top, all the secondary heat sinks are connected together to transfer away any disturbances from the surrounding. Also, to minimize heat flow, all the samples which are in the A sides are positioned on the outside, and we have the inert references pointing towards the middle. And then this calorimeter block is put into the thermostat, which you see in the lower left corner is the whole thermostat cut away. In the bottom part of the thermostat is all the control electronics and communication cards to the computer. It's a floor model, so the height will be approximately of a laboratory table. If we look at the right picture, we can see how the calorimeter block sits inside the thermostat box where the air is circulating. It's actually 2 boxes, so you have one box where the air comes in and flow on all sides of the calorimeter, and then it overflows and go on the outside of that box down to the temperature control part of the thermostat. In this way, we also are able to shield from external disturbances. And then you have the calorimeter, you have the thermostat, and then you need to put the sample into something, and that's what we call our sampling handling system. We have static ampule, which means that we are not doing anything with the sample after we put them in the calorimeter. We put them in an ampule, put them into the calorimeter and measure what's going on. They are available in glass, plastic, and stainless steel, and both for the 125 and for the 20 milliliter calorimeters. For the 20 milliliter calorimeter, the 8-channel standard volume calorimeter, we also have what we call the admix ampule, as I mentioned, and that's possible then to add and mix samples inside the calorimeter. It can come with manual stirring or with a motor stirrer to be able to stir the sample inside. If we have a closer look to the admix ampule, which is used for early reactions, is that in the bottom you put your sample to be mixed, and this part with the glass ampule in the bottom, that's what sits inside the calorimeter. Above we have a heat sink lid, and that's the lid that sits in the secondary heat sink of the calorimeter. The syringes, which could be 1 up to 4 1 milliliter syringes, sits in the thermostated part of the thermostat, and then you have a thermostat lid above the syringes. In this way, the liquid you're injecting into your sample is at the same temperature as the sample inside the calorimeter. Above the thermostat lid, we have the manual injectors, where you can push down to inject the sample into the ampule. And in this picture, we have a manual stirrer, and that could move up and down and also rotational, so you can get a very good mix of a cement sample. The motor mixer will just be rotational stirring if you put the motor on the top. And the height of the stir can be modified to fit that particular sample. If we look at the TAM Air Configurations and Specifications, we have the the TAM Air 8-channel standard volume calorimeter, where you have 20 milliliter calorimeters, and you have the 3-channel large volume calorimeter, where you have 325 milliliter calorimeters. We do specify the thermostat is the same, so the temperature stability is the same. But what is different now, or what we do specify, is a baseline stability over 24 hours. This specification doesn't mean that the temperature is constantly drifting every 24 hours. It's more that it's based on the 24-hour cycle of a room temperature variation. And the baseline stability is actually much better than you see on this specification, because if you elongate the time, you will see that the baseline stability is essentially 0, which can be seen in the next example with the data of TAM Air, real data that's been measured for several days, and we can see that the drift is nanowatt per hours, and that's measured for several days or up to a week. So we have nanowatt drift per hours or day, even if you can see some fluctuations within a 24-hour cycle. What is new also with the new TAM Air is that we have possibility to collect other signals to make the measurement more specific. You can configure your TAM Air with external probes, and the signal from this probe can be connected to the accessory interface and collected data at the same time as the heat flow data. In this way, you make the non-specific heat flow data more specific if you can connect it to maybe a pH probe, oxygen probe, to see what's going on inside the calorimeter. So in the accessory interface, you can connect what we call the voltage in-out box, where a voltage signal from any of these user-configured probes could be collected at the same time. As well as we have a pump control module, where if you need to pump fresh air or medium through the ampule, it's possible to control that also from the software itself. So if we look at TAM, I never mentioned, but TAM is thermal activity monitor, so we measure the thermal activity of a sample inside the calorimeter. TAM Air, I said that's a microcalorimeter, but we can go up to milliwatt ranges in measuring. So it's a sensitive calorimeter. It has a temperature range up to 90 degrees. It's flexible in the sense that you can change the calorimeter block inside the thermostat. You have different sample sizes you can use, and you have a 3 and an 8-channel calorimeter. But for some cases, for some applications, the sensitivity of the TAM Air is not enough. Then we do also have the TAM 4. It's the more flexible calorimeter. It has much more sensitivity. It goes over the whole sensitivity range, back to nanowatt sensitivity. And this is a completely modular system that you can build up to your own needs, from very small samples below 1 milliliter up to 125 milliliter samples in this case. So depending on the needs, there is the TAM Air, which is perfect for cement and concrete and food applications. If more sensitivity is needed, there is also the TAM 4. So that was the instrument, and now I move to the applications. And since cement and concrete is the far biggest application of the TAM Air, I will start with that as one application area. TAM Air is an excellent tool to measure the total heat of hydration, as well as to continuously follow the reaction rate in the different phases of the complex cement hydration process. The heat flow profile from an hydrating cement or concrete is information rich and can be used for and to aid in the development of new cements and admixtures, dosing and formulation optimization. It could be used to study the temperature impact of the cement hydration process, to detect any incompatibility between materials, and it's also used in production and quality control. The heat flow signal can look like this. So the shape of the heat flow versus time will reflect the different processes of the hydration of the cement. And an effect of an admixture that's added to a cement or concrete will then be reflected in a change in the hydration curve. And the integrated heat flow curve is the energy involved and is related to the extent of the reaction. In this plot, the blue one is the heat flow curve, where we can see the different processes going on, and the red one, there's actually duplicate samples of these. The two red curves is the total heat that is produced over the time. So if we look at the cement hydration process, it could be divided into several steps. First, we have the initial rapid process, where the initial dissolution and the start of the hydration process starts. That's very fast and is usually within the first 30 minutes. And then we have the dormant period, which is associated with a low heat evolution and slow dissolution of the silicates. Then the acceleration period starts, where the hydration process takes off, and that's called the main hydration peak. And then after that, we have the retardation period in number 4, where sulfur depletion occurs and the slowing down of the whole hydration process. And then there are long-term processes from after a day or two and up to weeks. You can follow long-term reactions in the cement or the concrete as well. There are 2 ASTM standards associated with the cement. We have the C1702, which is a standard test method for the measurement of heat of hydration of hydraulic cementitious material using isothermal conduction calorimetry. And conduction calorimetry is the same as heat flow calorimetry. And this method stays 7 days measurements for the heat of hydration with or without internal mixing. And this method will give you equivalent results to the solution calorimetry ASTM method C186. I can have some notes on the sample size and the sensitivity of a calorimeter for measuring these 7 days of hydration from a cement. In the method, it states that the cement sample or the temperature in the cement sample should not increase more than 1 degree from the thermostat temperature. A larger sample may not comply with this method, as the heat produced when the cement is hydrating, it could warm the sample up, and hence the measurement cannot longer be considered isothermal, as well as the kinetics of the process will be affected. But the sample needs to be large enough to produce enough heat to be measured reliably after 7 days. So the benefits of TAM Air in this case is that TAM Air has a high sensitivity. Even smaller samples will give a reliable signal after 7 days. And the choice of 2 sample volumes, 125 or 20 milliliter, you can optimize depending on the sample which type of calorimeter you are going to use. The 8-channel standard volume calorimeter is perfect for the cement or mortar hydration measurements. Then you can utilize smaller sample. If you have concrete samples, the 3-channel calorimeter is a better choice, where you can use bigger sample to get whatever aggregates you have in the cement also and get a more representative sample. Then there is the second ASTM standard, 1679, which is a standard practice for the measuring hydration kinetics of hydraulic cementitious mixtures using isothermal calorimetry. It will measure the relative differences in the hydration kinetics of a cement paste or mortar. The data is graphically and mathematically evaluated for retardation and acceleration effects. It's also stated that calcium sulfate may be added as a probe to see that there is enough sulfate to start with in the cement. And there we have some examples from the method itself. How it's graphically produced to see that the hydration profiles are different. For early hydration, we say that if you're going to mix your cement sample outside for measuring 7 days of hydration, you can mix it in the ampule, put it into the calorimeter, but then you miss the first 10, 20 or 30 minutes of the hydration process, depending on how high the signal is. If you're interested in this first signal, then you should use the admix ampule. In the admix ampule, you will put your cement powder into the ampule, and then you will add water and mix it inside the calorimeter. And then you initiate the hydration reaction inside the calorimeter to be able to measure from the first injection of water. In the example here, you see 2 samples, and you can see on the time scale now, no, we're not on days, it's the first 30 minutes you're looking at here. Another example is the temperature-dependent processes. The cement process is very complex, and it is affected by temperature. In the upper left curve, A curve, you can see 3 cement sample measured at 3 different temperatures. And we can see the higher the temperature, the faster the reaction rate. If we integrate this curve and go to the upper right curve, we have the extent of the reaction where we have the integrated heat flow. So we are plotting the heat versus the time here for the different temperatures. And now we can do Arrhenius kinetics from the cements. Either you will fit an overall rate constant to the process, or you can compare the heat flow or the rate of reaction at different extent of reactions. So to do that, you need to check the different extent of reactions. For example, you choose after 100 joules evolved heat, and then you go in the B plot to see at which time have I reached 100 joules. And then you can go in the A plot and take the heat flow rate at that particular extent of the reaction. The heat flow at this extent of reaction can then be plotted in a Arrhenius relationship, which is in the lower left curve. So at different extent of the reaction, you will have different heat rates. And heat rate, I see it's the heat flow we are measuring, which are directly related to the rate of reaction. So in a Arrhenius relationship, you can directly plot the heat flow you are measuring in a logarithmic form. And you plot that versus the inverse of the absolute temperature. And we can see that we get a lot of different activation energies out of this, and those are plotted in the lower right curve, the D curve. So we can see there are a lot of processes that's going on at the same or after each other in the cement hydration process. This is just 2 examples of hydration profiles with or without additives. In the first one, it's actually measured the cement in the 3-channel large volume calorimeter, where the red curves is a triplicate sample of a cement mix that's put into the calorimeter without any admixtures. A week later is the orange curve. We mix the same cement, but also in one of the 3-channel we add an accelerator, which is seen in the green curve, and a retarder that's seen in the blue curve, where actually nothing has happened. So by adding this, you can get a quick look of how the cement hydration profile is changing with additives. The second example is a concrete sample where a superplasticizer is added to the concrete before measuring. The green curve, both are duplicate samples. The green curve is without the superplasticizer, and the red one is with the superplasticizer. And we can see that the profile is changes with the addition of the admixture. So to summarize some features which is beneficial when you use TAM Air for the measurement of the cement hydration process, you have choice of 2 volumes, 20 or 125 milliliter, that will allow either cement and concrete samples to be measured with optimal performance. We have the availability of the admix ampules to allow the measurement of the initial reaction in the cement when water is added directly inside the calorimeter. It has a high sensitivity and baseline stability, which makes it possible to follow the hydration process for weeks. And it has multi-sample capacity for simultaneous analysis, and it conforms to the ASTM standard C1702 and C1679. So that was an overview of the cement and concrete application. Now I will move into other application, and they are grouped together, so I will give examples over the whole in the same part of the presentation. But you can find applications within a lot of different application areas, but the main one I will talk about is environmental science and food analysis. I mentioned to the start that calorimetry is a universal technique, and as almost all reaction and processes produce or consume heat, and that is what we measure, any changing system can be studied in a TAM Air, chemical as well as biological. So we can use TAM Air as a process monitor, a kinetic instrument, an analytical tool, and a general research instrument. And it could be applications within safety assessment, stability and compatibility evaluations, and quality control. So, the TAM Air is well suited for study of chemical and biological application in larger samples. Samples that are either physically large, heterogeneous samples, or samples that require a large headspace. So I can just list applications here that are included, but the applications are not limited to these. Food science, looking at spoilers and shelf life, fermentation, metabolism. We can look at environmental science, biological activity in soil and sediment, effect of wastewater treatment, soil or water remediation. In biology and microbiology, we can look at germination, small animal metabolism, and also used for microorganism detection. It can also be used in material science for looking at curing reactions, looking at safety assessment, and stability and compatibility measurements. And in battery science, which is part of material science, where we can look at battery efficacy and charge-discharge cycling. I will give a few examples of the different application areas here. Looking at food fermentation to start, we can follow the fermentation process in milk, beer and wine, in cheese, and in probiotic foods. So calorimetry can be used to study the properties of microbial cultures, such as we can look at differences between different cultures. We can measure the doubling time. We can look at influence of additives and the influence of temperature. So if we take the influence of additives, we can see in the top graph where milk is fermented and there are different sugars and salts and preservatives added, and we can see how the fermentation process is changed in time when adding these additives to the milk. In the bottom graph, it's shown the fermentation process as function of temperature. So the same milk fermentation is done at 25 and 90 degrees, and we can see that the fermentation process is faster at higher temperatures. We can also use TAM Air to study the biological activity in soil. This example will show soils from two different locations, and they're also with or without sugar amendment. Sugar is used to feed the microorganism in the soil, and we can see the soil quality can be determined from how well the soil microorganisms react to the addition of sugar, how they can utilize this substrate for their metabolism and growth. Epoxy curing is another example. Epoxy curing is a quite energetic process. You don't need very much epoxy to go into the system to be able to study it. In the first upper left graph, there is 4 samples run at the same time, so the reproducibility of these kind of measurements is high. This data has been done at different temperature, which you can see to the right graph, where they have been done with 5 degrees differences during the measurement. And we can see the higher the temperature, the faster the process, and more heat is evolved early in the process. In this case, we have done a Arrhenius relationship, but the top value of the heat flow is taken as the extent of reaction has come to the same process. So we can take the rate of reaction at the peak temperature, a peak maximum, and plot them in a relationship as in the lower left graph here. And we can see that if the reaction or the logarithm of the heat rates will fall onto this line, we can assume that the process is following the same. Sometimes going up in temperature, this will not fit on the same line, and we can see that the reaction process, the reaction kinetics has changed when coming up in higher temperature or lower temperature for that matter. And here we have an example of battery testing. In this case, a AAA battery was put into one calorimeter of the TAM Air, and then a resistor was connected to the battery and put in an adjacent calorimeter in the TAM Air, so we can measure the useful power that's generated by the battery. So the dotted line is the battery, so that's the internal energy that we measure from the battery when it puts out heat or power to the battery, the resistor we are measuring on. In the first top graph, we have a very low resistance connected to the battery, and we can see that the heat produced both in the resistor and in the battery is quite high, and the battery drains very fast. So this is 1 hour before the battery power goes down. And in the bottom graph, we have a much higher resistance, and we can see that the battery power lasts much longer, and there is not much heat produced either from the battery or the resistor that we are measuring. And that could last for then 40-50 hours with this resistance. So to summarize the power of TAM Air, generally we have multi-sample capacity for simultaneous analysis with 8 or 3-channel true twin calorimeters, each with a low noise, high sensitivity and excellent long-term stability. It's easy and robust operation. It's easy to change the 8 and the 3-channel calorimeter from each other depending on the sample needs you have. You have a sample flexibility with the choice of different ampere configurations, and you have increased measurement specificity with the external probes that's now offered with the new TAM Air. And if we specifically look at using TAM Air in the cement and concrete analysis field, TAM Air is a well-established within this field, and is considered a state-of-the-art calorimeter in several publications for just cement hydration studies. It has 20 milliliter sample volume to avoid temperature increase in the sample, which means that this is an essentially isothermal measurement. And the small samples also give a small time constant, so the different stages in the cement hydration process can be studied accurately. And the availability of the admix sample to study the early hydration reactions is also a benefit to be able to capture the whole hydration process of a cement sample. So, TAM Air from us. It's a versatile isothermal calorimeter with high performance and robustness, and if you got interested in this, please contact us. Thank you.
Thank you, Malin, for that informative presentation. A recorded version of this webinar will be archived and available online through the TA Instrument website. We will now begin the question and answer segment of the webinar. And again, please submit your questions through the Q&A window. We will do our best to answer as many questions as possible.
Thank you, Malin, for that presentation. We have a few questions that have come in by customers, and I think I'll start to go down the list and read them for you, and then listen for your responses. I'll just mention that for any questions that that have come in that we don't get a chance to answer on this particular webinar, we will answer them by email and make sure that we get to you the information that you need. So Malin, the first question that came in, it was about baseline stability. It basically asked the question, how critical is baseline stability to testing environmental samples?
Baseline stability is critical because we will, over time, if you're going to do an integration and see how much heat is produced over time, you don't want the baseline to drift away, so you will integrate from the wrong starting point or end point during the measurement. Samples can be run for several days to measure what's going on in an environmental sample with microorganisms growing. And if you're integrating this, you would like to know that your baseline actually is where you are, otherwise you will get a completely wrong number on the baseline stability. What is also critical is the precision of the instrument, because if you are measuring low amounts of heat, you need to be sure that when you insert a sample inside the calorimeter, that the signal that you get on your sample actually reflects the sample itself and not anything else that goes on by misplacing an ampule inside the calorimeter. And we know we have a very good precision on the TAM Air thermostat between samples.
The second question that came in, Malin, is one about calorimeter blocks. It says, can I move my existing calorimeter blocks from the TAM Air I have now to this new thermostat?
Yes, that is possible. Everything that you have on a previous TAM Air can be moved to a new thermostat. So you can move your calorimeter block, either a 3-channel or 8-channel calorimeter block, as well as all admix ampules that you might have can be moved to a new thermostat, and it fits and is compatible with old and new are compatible. The only thing that needs to be also complemented is a new lid to the new thermostat.
Here's another technical question, Malin. How critical is sample size for the calorimetric measurements?
If we now refer to cement samples or other samples as well, is that of course sample size is critical, that you need to have enough sample to have a detectable signal. But when it comes to cement or concrete, the issue is not to get too little signal, is actually to get too much signal. Because cement is a very energetic, the cement hydration is a very energetic process. So if you have a too big of a sample, the sample is actually heating up itself, and then the temperature of the sample could change. And if the temperature change of a sample, the kinetics of the reaction will change. So it's critical that you don't have a too big of a sample to heat up your sample as such. In some of the cement methods that are available, the ASTM standard C1702, it states that the cement sample should not increase in temperature more than 1 degree, because then it won't comply to the standard. And that, for very energetic cements, this could actually happen if you come up to 10 grams of sample, for example. So sample size can be very critical. And we also see that, well, we have heard the argument that in a real construction, when you do construction work where you have a big amount of cement or concrete, temperature will actually increase. So may it not be better to measure on larger sample where you see that temperature increase? But with isothermal calorimetry, where we measure, we have control over the temperature. So we measure at one fixed temperature, we can know the kinetics of the process, how much heat is produced. And we can measure at different temperatures to do Arrhenius relationships and see how temperature dependence is of that particular process we are studying. So we can simulate a whole concrete construction work, and we have control over the different temperatures, which is not the case if you get a too big of sample, because you have no control over the temperature in the sample when you have too big samples.
Malin, you mentioned just in passing in those few statements about method C1702. And in your presentation also, one of the customer asked that you sort of give a little bit more information about the method that says you can do it with or without internal mixing. And is there a difference, the customer asked, is there a difference in those two methods, and what is it?
There will be different if you, so with internal mixing means that in the TAM Air, you use the admix ampule and you add the water to the cement inside the TAM Air and you stir it inside. Then we actually have the whole reaction recorded from the additional water until the cement is hydrated. Without internal mixing, then you will mix your sample outside the calorimeter and you will lower the closed ampule already mixed cement paste into the calorimeter. Then you miss the first minutes of reaction. Also, when you lower your ampule inside the calorimeter, you will disturb the calorimeter slightly. So you miss the first 10 minutes or so from your reaction by mixing outside. The method C1702 says you can do either way. You could either mix it inside, get the whole reaction, or mix it outside and miss the first 10 minutes. And there could be a slight error, but the heat of hydration for the long run is so much bigger, so that error for most, for at least for Portland cements, that's a minor thing. If you have non-Portland based cements, you might need to do corrections of that afterwards, and that's Procedure who describes that as well.
Here's the last question, Malin, for coming from the customers, and I know there are a few more smaller ones, and I'll just mention to everyone listening that we will answer all of them. But this one has to do, you've mentioned a lot about cement, but this one is on the 8-channel calorimeter. Can the 8 channels be used independently of one another?
Yes. You can either do one experiment with all 8 channels together, or you can start every channel independently of each other. The only thing in common they would have is the temperature as they sit in the same block. But you can start every experiment at different times or as single experiments, or you can also combine 2 channels in each experiment. That's also possible. The only thing is that there could be, if you're measuring very, very small amounts of heat, you would like to start them close in time to each other. For a cement sample, it doesn't matter at all because there is so much heat involved in the reactions we are looking at.
All right, thank you very much, Malin, for answering these questions that came from the customer. And I'll just mention to everyone listening again that if we didn't get to your question, we'll certainly answer it by email. We have your email address. We'll try to make sure that you get the information. So once again, thank you for attending today and listening to this webinar on the new TAM Air thermostat.